Imagine every picture you took over the past year, all saved within the area of a single dot of ink from a ballpoint pen. Well, this is approximately how compact data is stored inside a hard disk drive. And in this video, we're going to open one up and see how an entire library worth of books is able to fit within the surface of this metal disk. We'll start by opening up this hard drive and detailing the components inside. After that, we'll dive into exactly how the drive stores data using the read and write head, and in the process, we'll look at the tracks, sectors, and magnetic domains of the metal disk. Finally, we'll explore some of the latest advances that enable over a terabit of data to fit within every square inch of the disk. This video is sponsored by PCBWay. More on them later, but for now, let's jump right in. On the inside of this drive, we find a variety of components. Here's the disk, or platter, that stores all the data, and depending on the storage capacity of the drive, might be multiple platters tall. The disk is composed of an aluminum-magnesium alloy with multiple coatings of other alloys, but the magnetic functional layer is this 120 nanometer thin layer of a cobalt-chromium-tantalum alloy, which has small magnetic domains or regions whose direction can be manipulated via external magnetic fields. The platter is mounted on a spindle which spins at a speed of 7,200 RPM, using a brushless DC motor at its center. Next, there's a head stack assembly, with one arm above and one arm below each disk, and with a slider and a read-write head at the end of each arm. The slider is uniquely designed such that it catches the airflow generated by the ludicrously fast-spinning disk and uses the airflow to float or fly the read-write head so that it's only 15 nanometers or about 100 atoms away from the surface of the disk. For reference, here's the thickness of a sheet of aluminum foil. Because the arm assembly flies on top of the spinning disk, it's only brought over the surface when it's at full speed. And when the disk is not spinning, the arm assembly is parked to the side on a small piece of plastic. Back here, a voice coil motor composed of a coil of wire and two strong neodymium magnets above and below is used to move the entire arm stack assembly. When electric current is run through the coil, it creates an electromagnet, which is influenced by the neodymium magnets, thus generating a force that causes the arm to move across the disk. When a reverse current is sent through the voice coil, the arm